I want to now define and illustrate what we call a standing wave. They're very important in nature, and they're kind of fun to watch visually. I will certainly demonstrate this for you. And basically, they're produced by just similar periodic waves, waves that are continuously produced, passing through each other. So if we have waves coming in opposite directions, then they can form a standing wave. Traveling waves moving in opposite directions. So here's our first wave. Our first wave looks like this. It's moving to the right, and it has amplitude A. Wavelength lambda. And we're going to have a similar wave going in the other direction. Moving to the left, amplitude A, wavelength lambda. And if you bring those in opposite directions, they interfere with each other on a continuous basis. They make a standing wave. Now, my graphical illustration isn't as good as the real thing, but an interesting feature of a standing wave is that it looks like it's standing there. Basically, these loops that you see are whopping back and forth, but they don't seem to be traveling. So that's pretty neat. Moreover, you probably know from our previous discussion, like when we put this crest on this crest, when they're on top of each other, they add, so the amplitude of the standing wave is 2A. And here still is the wavelength, right? That hasn't changed. All right, but there's a couple of, features here. The crest, the maximum amplitudes here. These are called the antinodes. Antinodes. There's a max displacement of the medium at those locations. Then there's a couple other key points, along the equilibrium position here of the medium. These places right in the middle are called nodes. And a node is a place where there's no displacement of the medium. And so there's no movement. Literally, when the wave is standing there, whopping back and forth, you can stare at this location. The medium doesn't move here. Because the result of both directions of these traveling waves moving through the medium is to keep these nodes motionless. So that's kind of awesome. So this is an example of what we call an antinodal loop. Antinodal loop. We got the antinodes, and it's a loop, and it continually stays as a loop. You can watch that loop. Now, standing waves have some characteristics. We already have considered that waves transfer energy. And so I just want to illustrate that again. So if a traveling wave gets reflected, the energy gets reflected as well and comes back. And that's continuously happening in a standing wave. So the energy is continuously maintained in the system in the form of kinetic and potential energy. And it's going between one and the other as these antinodal loops are whopping around, which is not a very technical term, but kind of how it looks. The only energy that has to be maintained to keep that going is the energy lost to frictional loss, basically. And, a moving medium typically has some losses. So here's three antinodal loops. And it looks like they're standing there. But really, this is going up to this side, this is going up to this side. They're just whopping back and forth. But it looks like the loops are maintained. They're not like moving to the right or left. That's the interesting thing. So what about the vibrating region between the two nodes? The nodes, that vibrating region is what we call the antinodal loops. And what is the length of one of those loops? Well, first of all, let's consider that, what a wave, this is one wavelength here, so that's lambda. And so an antinodal loop is 1/2 a wavelength. How many antinodal loops are there for one wavelength then? Well, obviously 2. 2 antinodal loops for one wavelength. All right. Now, I'd like to do an example of, you can actually determine the speed using a standing wave. We can figure out how fast the medium velocity is, namely how fast the wave travels, by looking at the characteristics of a standing wave. And I'll do that in class with a wave machine. And the results I'm just going to list here essentially, but you'll get the theoretical idea right now. So the number of antinodal loops we'll call n. So many antinodal loops there are in the medium. It's a finite medium from end to end, you know, from say here to here. In this case we have 3, but there could be more. So n is the number of antinodal loops along the length L. So here's L, the length of the whole medium. So L, this whole length, divided by the number of antinodal loops, however many they are, is the length per loop. Total length over how many loops? Length per loop. So that's lambda over 2, because the length per each loop is a half a wavelength. L over n gives you how much total length there is for how many total loops, but that ratio is lambda over 2, right? Same as this, the length of a single loop. Hopefully that's not confusing. Then when we have L over n is lambda over 2, we can solve for lambda, and it gives us 2 times the length divided by the number of antinodal loops. That's a wavelength. So we can determine the frequency experimentally. It's waves per time. And to determine the speed is frequency times wavelength. We've encountered that already. So now the particular data from the wave machine that we can use to measure this, the length is 9/10 of a meter for the wave machine. I can set up a number of antinodal loops equal to 4. So really this is just like an example. Make 4 antinodal loops in 0.9 meters. The wavelength is 2 times L, so 2 times 0.9 over n, 0.4, and that's 0.45 meters, so that's a wavelength. If there's 4 antinodal loops, that means 2 waves anyway. So 1 wave would be half of the total length, which is 0.45, half of 0.9. You can measure the frequency, and when we do that, we get the number of waves per time. We get, if we count 10 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, divided by the time it takes, in this case 9 seconds, gives us 1.1 cycles per second, 1.1 hertz. So there's the frequency. Now we're going to do wavelength. Speed is frequency times the wavelength. We have the data, 1.1 times 0.45, 0.5 meters per second. So that's an example of how we can use standing waves to determine wave speed in a medium. That may not have been so much fun, but it illustrates some of the ways in which this wave theory can solve problems for us. And we will conclude with that and move on to the next thing.